I am currently in the heart of one of the best-kept places in France. A restricted area with limited access. Inside the so-called European Pressurized Reactor Nuclear Power Plant of Flamanville. Just behind this door is the most powerful nuclear reactor in France. And clearly, unless you live in a cave, it's unlikely that you've never heard of it. This power plant, the first to be put into service in France in 25 years, has been widely discussed in the media. It's because of all the new technologies that are being deployed there. But also because the extraordinary construction project required for its construction has spread over nearly 17 years and has had to deal with quite a few budget overruns. Above all, you have everything concentrated here in the same place. Part of the answer to the question of France's future energy. So, when Électricité de France offered me to come and visit this reactor that has just been connected to the electricity grid, I immediately said yes. On one hand, because I've always wanted to see the inside of a nuclear power plant. It's also a chance to discuss the remarkable process we've mastered here, which enables France to generate 65% of its electricity. I'm discussing nuclear fission. Today, I will dissect the workings of this immense machine for you. And together, we will explore a nuclear pool, discover the main principles of a reactor, from the reaction that releases energy to the production of electricity. And visit a room that, with its hundreds of buttons and dozens of screens, allows you to control everything we're going to talk about. Before discussing the cost and safety of the future, which would make for a nice program. But before anything else, a little reminder is necessary about the why. Why do we spend so much time, money, and brain juice to develop and manufacture things that are so gigantic, costly, and complex to achieve? Well, the answer to this question lies in there. All the complexity of the engineering deployed in the vastness of these buildings is only there to recover the energy released by the fission of something as small as this. A uranium pellet like this one, well, this is a facsimile, but this is exactly what the real ones look like. A small enriched uranium pellet of this size only weighs 7 grams. And yet, it can release roughly as much energy as the combustion of a ton of coal. So much so that by relying on the absolutely exceptional energy density released by the fission of these small pellets, the power reactor of Flamanville is capable of covering the electricity needs of 2 to 3 million households on its own. The physical principle that hides behind the abilities of nuclear power plants to produce gigantic amounts of energy is quite crazy, almost magical when you take the time to stop a little to think about it. Because this extremely dense and compact energy source comes from the heart of some of the smallest elements in the universe, the atoms. You certainly know this since I repeat it often, as I never cease to marvel at it. But for over a century now, Einstein has shown through his famous equation E equals mc2 that mass and energy are fundamentally just two aspects of the same coin, and that under very specific conditions, one can be transformed into the other. And that's exactly what's happening here. A nuclear reactor is nothing more than a fantastic machine designed to make matter disappear and transform it into energy. The principle is as follows. We're going to use the properties of uranium atoms, atoms that literally pack a punch on the scale. Because these are the most massive of all the ones that can be found in their natural state on Earth. I'm going to detail the principles a bit, but if you want to dive into the technique, you can skip to 2 minutes later in the video. There are several versions of uranium atoms in nature. We talk about isotopes based on the number of neutrons and protons their nucleus contains. The most common are uranium-238 with 146 neutrons and 92 protons in the nucleus, and uranium-235, which, as its name indicates, contains a bit less, but which has the particularity of being unstable. In other words, the densely packed protons and neutrons at the core of these atoms are in a delicate equilibrium. Their binding energy is on the verge of breaking, so much so that the nucleus of these atoms is just waiting to explode. And when they are bombarded with well-calibrated neutrons, these overloaded nuclei will suddenly explode to give birth to two lighter atoms, while emitting radiation and new neutrons. Neutrons that can in turn, if conditions allow, cause other nearby uranium nuclei to explode. and thus initiate the beginning of a chain reaction during which each fission of a uranium nucleus releases large amounts of energy while causing new bursts. And as strange as it may seem, every time the heart of an atom is broken into two smaller pieces, the sum of the masses of the two newly formed atoms and the new ejected neutrons is always less than that of the original uranium nucleus. Because with each burst, a part of the cement that's in the form of binding energy holds together the protons and neutrons of the uranium nucleus, contributing to giving it its mass and transforming into radiation, into energy. And if this amount of energy that is released is insane, it's because it is equal to the lost mass, multiplied by the speed of light squared. Yes, I know, nature is completely crazy. However, even if the mass difference is minimal each time, when we multiply it by the speed of light multiplied by itself, we get a prodigious value. In fact, the fission of a single uranium atom releases an amount of energy several hundred million times greater than that released by a chemical combustion reaction, involving, for example, a methane molecule. And in a pellet like this one, there are nearly 40,000 trillion uranium atoms. That's a lot. And that's why a nuclear reactor, such as the European pressurized reactor, only needs to fission a negligible amount of material per year to power 2 million homes with electricity. In fact, we can even calculate that, on paper, a reaction of this type is capable of injecting into the grid as much electricity every hour as would be produced by the combustion of some 160 cubic meters of oil. To put it another way, to release as much energy as the European pressurized reactor can theoretically produce, operating all year round, you would need to burn a volume of oil equivalent to that contained in 3 supertankers filled to the brim. In brief, uranium's energy density is utterly astounding. And it is precisely to be able to control this chain reaction and recover the heat released to transform it into electricity that we build nuclear power plants. And you will see that if the amount of fissioned material is relatively negligible in volume, all the infrastructure surrounding it is absolutely gigantic. To convince ourselves, we're going to take a step back to observe the entire site from the air and thus get an overview. I won't explain exactly how it all connects. But what you need to remember here is that the reactor building where the uranium is fissioned and which you can see here, it's just a very small part of a much larger whole. Because a nuclear power plant is literally a small town comprising dozens of buildings, with their mazes of cables, tubes, turbines, each with a very specific role, and under the hood of each of them hides a megalithic trend in engineering craftsmanship that had to be thought out, designed and built. The most impressive is surely the reactor building of which you see here stages of the construction, and whose vessel, equipped with a lid weighing 145 tons, is topped by a culminating dome, at 60 meters high and surrounded by a watertight containment enclosure made up of a double wall of 2.50 meters thick of reinforced concrete, itself covered with a steel skin, designed to withstand major accidents that could occur inside. Here, we discuss the fusion of the core or outside, while there, we discuss a commercial airplane crash. I wanted to show you the reactor, but reactions have begun inside. For safety reasons, we couldn't go there. However, the pools that are just behind me are a very good starting point to explain to you how all this works.
So here we are in the fuel building. This is the building where we received the fuel, where we arranged it to put it in configuration to be able to do the loading. So it's a building, there are 960 alcoves in the back, there are about 15 meters of water, 15,000 cubic meters of water. So it's water with a chemical product, with an edge, which allows the assemblies to cool down, and also to limit the chain reaction when there is radioactivity.
Because this is where we store them for several years before sending them to the reprocessing plants. The spent fuel rods, that is to say those that have already passed through the core, well, there aren't any yet, since the reactor hasn't been running long enough. And we also store the new fuel rods there, and waiting for loads which are used to power it. If we store the rods underwater, it's because it acts as a protective screen against radiation and also allows for the cooling of used fuel assemblies. Okay, now, we're going to try to imagine the absolutely phenomenal amount of energy that we can recover by inserting these stored fuel assemblies into these pools. In the heart of the reactor, you'll see it's fascinating. In the heart of a nuclear reactor, such as the European pressurized reactor, we generally insert 241 fuel assemblies, and each of them is made up of a cluster of 265 rods that we call pencils, and inside which are stacked about 250 enriched uranium pellets like this one, each capable of releasing, remember, as much energy as the combustion of a ton of coal does. So the calculation is easy to do. In the core of the European pressurized reactor, you have essentially stored as much energy as would be released by the combustion of 16 million cubic meters of coal. To give you a picture, if we were to gather this colossal volume of coal in the same place, we would end up with a pile 18 times larger than the Great Pyramid of Giza. Once the reactor core is loaded with fuel to recover energy, the chain reaction must be started and controlled. The general principle is as follows. We ensure that only one of the neutrons emitted each time a nucleus bursts causes a new fission. And for this, control rods are introduced into the reactor that allow a large part of the neutrons to be absorbed and thus control the reaction. Movable rods made of neutron-absorbing materials slow down fission rates by their presence. If we want to reduce the amount of energy released or even stop the reaction, we push them deep into the core. And conversely, when we need to produce more energy, for example during peak electricity consumption hours, in the early morning or evening, when many people are using appliances, we raise them. In case of a problem, these control clusters have been designed to fall automatically and thus stop the reactor in a few seconds. And there you have it, in an extremely simplified way. How can we vary the power of a nuclear reactor? Then, this energy released in the form of heat, it must be transported out of the reactor core to systems capable of converting it into electricity. These are the turbines and the alternator. In France, all of the nuclear reactors that produce electricity are pressurized water reactors. In this sense, like absolutely all traditional thermal power plants, they heat pressurized water to over 300 degrees, which is then relaxed and transformed into steam. The steam turns turbines, which in turn rotate generators that produce electricity. You get the idea? So right behind me there you have several Arabian turbines. The whole thing weighs several hundred tons, and each turbine spins 1500 times per minute and is driven by the incoming steam. So, in fact, this block, it receives all the power that is produced by reactor number 3 by the European pressurized reactor of Flamanville, and it allows to supply almost 2 million people with electricity. I'm convinced you didn't understand anything I said because even I can't hear myself speak. So, I'm going to explain this to you in the studio. It must be said that when the power plant is near its full power, every second, under 155 bar pressure, these 27 cubic meters of water are heated to nearly 300 degrees Celsius in the primary circuit of the reactor building. This nuclear heated water circulates in a closed loop, transferring its energy to the secondary circuit water through thermal exchange, whose steam will drive the turbines, which in turn will drive an alternator producing electricity. Do you still have the idea? From this perspective, it's interesting that nuclear power plants are still at the end of the chain. Highly sophisticated large kettles that convert thermal energy into mechanical energy, which is then converted into electricity. With an energy efficiency of 38% output, the European pressurized reactor allows for the development of 1,600 megawatts of electrical power. To give you an idea, it's on a scale comparable to what a large hydroelectric dam, such as the Hoover in the United States, can provide, or equivalent to the combined capacity of 2 to 3 coal-fired power plant units, or even 400 to 800 wind turbines. Except that dams or wind turbines are incapable of producing energy continuously. Let's clarify that the water you see coming out of the cooling towers of power plants built on the riverbank has never been in direct contact with the reactor core. And it's the same for power plants like those in Flamanville, which are by the sea and are therefore cooled by seawater and therefore do not need cooling towers. Here, we are in a gigantic simulator, the exact replica of the control room where the engineers who operate the reactor come to train. The airplane cockpit appears larger with numerous buttons, screens and switches, making it overwhelmingly complex. I can't even imagine the size of the manual.
So indeed everything happens from here, the control room. So here we have a console of an operator who can then choose the images they want to see. depending on what they want, the phases on which they will start the reactor. So one of the basic elements will be to obtain a chain reaction. So we will use two main means to generate the chain reaction, which will then be the lifting of our control bundles and the dilution of the reactor, the lifting of the bundles. Here we can see in the picture, for example, that the bundles are at the top. And so we will dilute to effectively reduce the edge concentration. This will allow to absorb fewer neutrons and to be able to start the chain reaction.
With a few exceptions, everything you just saw applies to all nuclear power plants in France. So, one might be tempted to think that the difference with other power plants lies in the power output. Once fully operational, the European pressurized reactor will be France's most powerful nuclear reactor. However, the difference is less pronounced when compared to the two previous generation reactors adjacent to it. Each can provide 1,330 MW of electrical power compared to 1,600 for the European pressurized reactor. What makes this reactor special is that it's the first to be started up in France in 25 years. The European pressurized reactor is a new third-generation reactor that is slightly more powerful and, most importantly, has enhanced safety features and additional safety levels.
So the European pressurized reactor, compared to the reactor of the existing park in operation in France, is not a revolutionary reactor. It uses exactly the same principles for
Produce,
transform. In fact, the energy from nuclear fission into electricity. So from this point of view, there is no innovation. The plus of the European pressurized reactor is that we have significantly strengthened its safety. The number one goal of the European pressurized reactor is to have a reactor by design, which is safer.
So undeniably, the European pressurized reactor improves what we were doing before. But it's less the technical improvements that made it famous than the fact that its construction was significantly delayed and that it caused the final budget to skyrocket. Delays in themselves are common in such pharaonic scale construction projects. We're talking about 400,000 cubic meters of concrete here, interspersed with 7 times the weight of the Eiffel Tower in metal reinforcement. That's only for the main work. A 12-year delay isn't that unusual. The Channel Tunnel took 6 years to emerge from the sea. The Sydney Opera House was 10 years behind schedule, and the James Webb Telescope 14 years. More than the delayed start, the explosion in total cost has been much discussed. Much could be said about the reasons for the slippage. I'll give you the one most often put forward. The European pressurized reactor is a lead series reactor, a huge piece of engineering, undeniably one of the most complex and ambitious projects of recent decades. This unprecedented project has been through a lot of mill. One element often pointed out is the fact that we have somehow forgotten how to do things efficiently. Because, in the prolonged absence of new construction projects in this field, the industrial fabric has unraveled and some skills, some know-how have taken time to get in tune. It's partly for this reason that all European pressurized reactor projects worldwide have seen their initial costs skyrocket. That's the bad news on the checkbook side. The good news comes from security. Because if the project has been delayed so much, it's because there is an independent body, the Autorité de Sûreté Nucléaire, the Nuclear Safety Authority, who regularly and unexpectedly comes to check that all parts are perfectly in line with the expected specifications. When that's not the case, we revise and start over. And this applies to all European pressurized reactor power plants, including... The second good news is that we still have, in the end, a new reactor, more secure, producing low-carbon electricity in large quantities. And that we should learn from our mistakes, since now we know in broad terms what not to do. And we can reasonably think that the 6 to maybe 14 other EPRs that should be built in France by 2050 will not experience such a budget overrun. Whether we like it or not, in the land of enlightenment, nuclear power is a subject that concerns us all. In 2024, out of the 438 operational nuclear reactors globally, 99 are in the United States and 57 are in France. I know there are some of you, hello mum, who see this as a curse, inherited from political choices and energy strategy dating back to the post-war period. I view this as an opportunity and part of the solution. Thanks to nuclear power in France, 65% of our electricity comes from an energy source that emits virtually no greenhouse gases. It's a unique case in the world. Try to think about it every time you turn on the light or a kettle. Renewable energies such as solar or wind require a lot of metals, and above all, they are intermittent by nature. Can we afford to do without a source of energy that operates without emitting carbon dioxide while being controllable? Having electricity even when the wind is not blowing or there is no sun is still very convenient. The Germans, who decided to close their nuclear power plant, had to subsequently open gas and coal power plants to compensate. To those who doubt that the upcoming energy transition will be challenging, here are some figures to remind you of the scale of the challenge. At the current rate of consumption, we have half a century of oil left, a few more decades of gas, and far too much coal. And the majority of these fossil fuels. It would be better not to use them.
Touch them, don't
Ever burn them and leave them underground if we don't want to get caught. 2 to 3 degrees increase in the average global temperature in a century. In France, even though we are lucky to have 97% decarbonized electricity, largely thanks to nuclear power, 60% of all the energy we consume still comes from fossil fuels, and absolutely all. All scenarios that envisage achieving carbon neutrality by 2050 foresee at least a doubling of the share of electricity in our final energy consumption. In summary, there is no secret to producing large quantities of decarbonized electricity. We will have to persevere in what we know how to do, namely nuclear, while developing all possible renewable energy sectors in parallel. Especially since if you set aside hydroelectricity, for which we no longer have much installation margin, we only have nuclear to provide electricity on demand. The energy transition is the global challenge of the 21st century. And at a more local level, at the scale of France, it is also a crucial question of sovereignty. I don't know about you, but I'm not a fan of the idea of filling the pockets of the oil monarchies of the Gulf or Russia every time I fill up. By the way, in 2023, fossil energy imports alone accounted for half of the French trade deficit. And since the European pressurized reactor is in Normandy, I would like to end this video with a little camembert. Here, you have represented in percentage the primary energy consumption in France in 2023. There, we can see nuclear, here all the renewable energies. And these are the fossil energies that need to be slimmed down to almost disappear over the next few decades. I think you see the magnitude of the subject.